Alright guys, so I'm going to film an example doing problem number 1 of that problem set with the inclines. So problem number 1 looks like, we'll draw it up here. I'm going to draw this kind of big so that we can, because of the way that we're doing Freebody diagrams. Problem 1, we've got ramp problems this time, right? Got a box up here at the top of the ramp. Actually, I'm going to put it down a little bit so that I can draw it. Good. I'm going to put it like right here. Box right here. They give us the angle of the ramp, 40 degrees, and they give us a, I guess I'll draw it like this. They give us the length of the ramp here, which is 20 meters. And the problems are asking for the acceleration of the box as well as the time that it takes for the box to reach the bottom point down here. That's what we're solving for. Great. First step in any forces problem is a Freebody diagram. So remember, for these, since they're on an angle, we talked about how it is to your advantage to draw the Freebody diagram at an angle. So I'm going to just show you both things. I'm going to draw it down here, straight up and down, and I'm going to draw it on the box at an angle so that you can see both of them. So I'll draw my axes, one right here, and then one right here. And our goal, we're drawing them parallel to the surface of the ramp, which we've found is the easiest setup. So, and then I guess I'll draw them down here also for reference. If you hear any construction noises in the background, I'm sorry. They're renovating the unit next to ours. All right. So, what forces are acting on this block? Obviously we have our first and easiest one, gravity, which is acting straight down, right? Gravity is acting straight down towards the center of the Earth, Fg. And for reference, you see how this one is located between these two quadrants, right? So what that would look like is this right here, off at an angle. And remember, I showed you the proof using fun geometry, alternate interior angle kind of stuff, that this angle right here is also our 40 degrees. This angle right here, if it's hard to see on the other one, 40 degrees is right here. You can either ask me for the proof or take my word for it, but it's this angle that you form with that, what is usually the y-axis, right? So that's gravity. In this case, there's no information about a coefficient of friction, so there's no friction force here acting up the ramp, but we do of course have the normal force of the ramp acting perpendicular to the surface, normal to the surface, Fn, and down here, right, perpendicular to the surface along that axis right there, Fn. And that's all acting on this one, just gravity and normal force, no friction, because we don't get any information about that. All right, step 2 in any force problem is to write sum of forces. So net force, in this case, is the box accelerating? Yes, right, it's accelerating down the ramp, it'll be picking up speed due to gravity. So it's not equal to 0, it's equal to mass times acceleration, F equals ma. Remember, if it were either not moving or if it were moving at a constant velocity, this would be 0, but in this case it is accelerating, so we put F equals ma. So then we write our net forces here. Now what we're concerned about, right, I should have added this before, is in this case, our direction that we're concerned about is not our up and down here, right? We know it's not accelerating in this direction. We're concerned about how fast it's moving down the ramp, right? So we're really just concerned about what we've labeled as our x direction here, our sum of forces in the x direction, right? So our only force acting in the x direction here, right, is our x component of gravity, right, in this direction. Or to say it down here, right, this component right here. I'll draw it in both places so that you can see. Like that, it's on the x-axis, right? I just drawn it down here because that's the triangle we'll be using in a moment. So it's really just this FGX, right, x component of gravity that's in the x direction. So our net force is equal to FGX. All right. We can solve for FGX. I'll just move this down real quick because we'll use it again. MA is equal to FG first. I'll just take the extra step to write that, I guess. So the x component of gravity is equal to gravity. We're looking for x right here, right? So we've got our angle here. It's opposite, right? So we use sine, opposite over hypotenuse, sine of our theta, which is 40, right? So to simplify this a little bit more, we may Fg, right? Force of gravity acting on an object is just mass times acceleration due to gravity, right? Fg equals mg. Sine of theta. Notice it didn't give us any information about mass here, but handily it's because they cancel out. So now we can plug values in and solve for a, because we know g and we know theta, because theta is just this angle here, right? So g, I'll be using 9.8. I believe the answers that were in the book there use 10 for simplicity, but I'll be using 9.8 because 9.8 is good. And our theta is 40, right? It's just that angle right there. So 9.8 times the sine of 40 is 6 point something. 6.3. So our acceleration is equal to 6.3 meters per second squared. That's step one, right? We got acceleration. Now we need to figure out the time that it takes for the box to slide down here. So this is just a good old 1D kinematics question. I'm going to rewrite our givens over here because it'll make it doing that matching, that equation picking matching game a little bit easier. So we just figured out that acceleration is 6.3 meters per second squared. We also have, right, the distance that it slides down, right? We have delta x here, which is 20 meters. We're looking for time, so we know we have that. And last but not least, this one, the problem statements say that if it doesn't give you any information, you're assuming the box is released from rest. So in this case, v0, our initial velocity, is 0 meters per second. Great. So we have our four chosen, right? Our three that we have and our one that we're looking for. So if we have three, then we can pick an equation. And so the one that we pick, you would have your formula sheets handy, but the one we would pick would be the one that looks like this. Delta x equals v0 delta t plus 1/2 a delta t squared, right? Because we have delta x, v0, and a, and we're looking for delta t. So this has everything we need. Then we just plug in. Easy as that. Matching and plug in, friends. Delta x is 20 m, v0 is 0 meters per second, delta t, so this goes away, right? 0 meters per second. Plus 1/2, our a is 6.3 meters per second squared, delta t, I'm running out of room here, delta t squared. Great. Then you just do some maths, right? So I need to divide by 1/2 times 6.3 on each side, and then I need to take the square root. That's just two operations, right? So I'll just skip ahead to the answer here. 20 times 2 divided by our 6.3 number, take the square root. I got 6.35 rather, and then you take the square root of that, which is 2.52 seconds. Ta-da! That's all I was looking for. Acceleration and time. We're just doing unit 1 and then, unit 2 and then unit 1. Do some force analysis, then do some equation picking with 1D kinematics. Hope you enjoyed. Bye.